Good morning, friends. Today I like to discuss about the position and change in Fermi levels. Whenever we talk about the positions, then we will consider about the nature of charge carriers, and the position depends upon the nature of charge carriers. So we consider it the nature of charge carriers in semiconductor can be classified as two ways. First case, when the effective masses are identical. That is, Mn, effective mass of electron, is equal to Mp, effective mass of proton. So from the expressions of electrons and holes, we have N of E must be equal to N of PE. Same. So if the expression is 2h cube, 2 upon h cube, 2me, that is mn star pi kt 3 by 2 e raised to the power e minus ec upon kt is equal to 2 upon h cube 2 mp star pi kt 3 by 2 and e raised to the power ev minus ef by kt. So from this term is 2 upon h cube cancel. This whole expression is cancelled because we have mn is equal to mp. So the remaining terms is ef minus ec upon kt is equal to ev minus ef upon kt. Or if the exponentials are same, then we can say that power is same, that is ef minus ec upon kt is equal to ev minus ef upon kt. Or this is ef sorry, minus ec is equal to ev minus ef. So this negative ef is transferred from right side to left side. So this is 2ef, and here ec is transferred from left to right. So this is ec plus ev, and this expression gives that ef is equal to ec plus ev by 2. ec plus ev by 2, that is mid level in between ec and ev. So the first case, so that Fermi energy is in between EC and EV. If this is EV and here it is EC, this is the valence band and here it is conduction band. So the Fermi level lie in between these two, that is EF, that is EF. So this expression can be represented in the diagram as. So this one is the first case. Now the second case is case 2, when Mn star is not equal to Mp star, that is effective masses are not same, then what will happen? So the effective mass from the expression from the expressions we have NPE is equal to so this is 2 by h cube 2m n star pi kt 3 by 2 e raised to the power ef minus ec by kt is equal to 2 by h cube 2mp star pi kt 3 by 2 e minus ev minus ei upon kt. Why we take here it is ei? Because we don't know what will be the change of E in reference to the mass. So again, we have the cancel part which is common. This cancel part is common. Again, the 2 is also common, cancel. So what we find? We find Mn star 3 by 2 e raised to the power ei minus ec upon kt is equal to mp star 3 by 2 e raised to the power ev minus ei upon kt. This one. So we can transfer this whole, that is e to the power ei minus ev minus, this is ev minus ei, this minus minus plus upon this kt is equal to mp star upon mn star to the power 3 by 2, to the power 3 by 2. Take log of both this side. Take log of both the sides. We have what we have. This is 2ei minus ev plus ec is equal to 3 by 2 natural log mp star upon mn star 3 by 2. Or what is EI? EI is equal to EV plus EC by 2 plus 3 by 4 ln mp star upon mn star 3 by 2. 3 by 2. This is the intrinsic semiconductor, and EI is the Fermi level. Now, if we like to draw, then we can have the case that is EI, this is EI is equal to EF, as in the case 1 plus 3 by 4 ln mp star upon mn star mn star. Now, if we analyze, that is mp star is greater than mn star. That is, effective mass of hole is greater than effective mass of electron. So what will happen? Then EI is greater than EF, because this thing is positive. This thing is positive and EI is greater than EF. When MP star is less than MN star, that is effective mass of electron is greater than effective mass of hole, then EI is less than EF. That is the Fermi level. So this Fermi level will shift. This Fermi level is shift in between the forbidden band, in between the forbidden band in different cases. So this one is the analysis of the case when these are not identical. Now the second term is law of mass action. Law of mass actions. In law of mass action, we have for the intrinsic carrier density, Ni. So Ni square is equal to N of Ne into N of Pe multiplication. So what we find, this is N of D e raised to the power minus Eg by 2 kT, and here it is N V e raised to the power minus Eg upon 2 kT. So what we have, Nd into Nv into e raised to the power Eg upon kT. This is Ni square. So Ni is equal to under root of Nd Nv into e raised to the power minus Eg by 2 kT. Eg by 2 kT. So this is valid. This law of mass action this is valid in both the cases. In both the cases, that is intrinsic and extrinsic semiconductor. Extrinsic and extrinsic semiconductor. at the thermal equilibrium, the ND and NV are effective density of electrons in conduction band and holes in valence band, respectively. Valence band, respectively. So these are two basics, important things that we have to discuss about the shifting of Fermi levels. Now we can have the variation of Fermi level in N-type semiconductor and P-type semiconductor. The expression, first equation, that is N is equal to ND e raised to the power minus EC minus EF upon 2 kT upon 2 kT. So, or you can see EC minus EF, then 2 is not required because this is the half itself, this value. So what we can express here, this ND EC minus EF by KT. So log NN by ND is equal to minus EC minus EF by KT, EF by KT. Or if you absorb this minus sign, so what will happen? This is EF minus EC by KT, EC by KT. So what we have, this is EF is equal to EC plus KT ln this one. Or we can have this EF is equal to EC minus KT ln ND upon NN. ND upon N. This equation. And this equation say that the Fermi level is below EC when this value ND is greater than NN. That is EF, that is Fermi level, is below conduction band. Below conduction band. And we can draw this case. Suppose this is valence band, this is conduction band. This is valence band and this is the conduction band. Here it is f of E, this is E, then the Fermi level is something like this. Fermi level is something like this. Here it is somewhere EF. So this is rising. This is rising. Now, in case of p-type semiconductor, as in case of n-type semiconductor, expression is n of p is equal to n of v e raised to the power minus Eg by 2 kt or nv e raised to the power minus EF minus EV upon KT. EF minus EV upon KT. So this N of P upon N of V is equal to e raised to the power minus EF minus EV upon KT. So taking log of both the side, so this is log of NP upon NV is equal to minus EF minus EV upon KT, and this is, if you observe this, so this EV minus EF upon KT. So this EF Fermi level is equal to EV, this is EV plus EV plus, or initially it was minus, EV minus log this is KT log NP upon NV or EF is equal to EV plus KT log NV, that is coefficient of N of P, this one. So this indicates that Fermi level is, that is Fermi level is above the valence band, and the diagram can be shown as F of E, here it is E, this is EC, this is EV, then we have this diagram, that is, this is Fermi level, and here it is lowering of Fermi level. So this EF P, and here it is EFN and EF. So what happened in this case, as we have discussed the by doping of the pentavalent and trivalent, when there is a formation of p-type, n-type semiconductors, then the Fermi level will change, shift Fermi level. And the final is degeneracy. Degeneracy of the material and energy level. Which energy level is Fermi? Fermi level. How to draw the degeneracy case? Very simple way we can draw. This one is N type, that is E, V and EC. Here it is P type, EV and EC. This is P type. Now we have shown the rise of Fermi level up to the conduction and above the conduction, and above the conduction. And if this will be the case, that is E dash Fn, means Fermi level is above the, that is EF dash n is greater than EC. Fermi level is above the CB, conduction band. Above, yeah, we can say this is EC, above the EC. Fermi level is above the EC. Here, Fermi level is lowering, and this is below the conduction level. That is E F P dash. This is E F dash P. E F dash is less than EV. Fermi level is below the EV, बैलेंस बैंड से नीचे. तो दो स्थिति क्रिएट हो रहा है, एक कि फर्मी लेवल कंडक्शन बैंड से ऊपर चला गया और दूसरा फर्मी लेवल वैलेंस बैंड के नीचे आ गया, वैलेंस एनर्जी लेवल से नीचे आ गया. ये so these two cases are known as degenerate case. These are known as degenerate cases. How it is possible? Mathematically, if we see, we can have, this is EFN. EFN is EC minus KT ln ND upon NN. So in this case, ND upon NN, the donor and the charge available is of these three cases. When N of D is greater than N of N, number of dopant and the number of dopant is equal to NN. This is ideal. This is ideal case. This is ideal case, and here it is real case. Real case कि जो कैरियर इलेक्ट्रॉन का कैरियर कंसंट्रेशन होगा, वो कैरियर कंसंट्रेशन, इलेक्ट्रॉन का जो कैरियर कंसंट्रेशन होगा वो डोपिंग एलिमेंट के कंसंट्रेशन से कम होगा. और कम क्यों होता है? इट इज ड्यू टू द क्रिस्टल डिफेक्ट, इट इज ड्यू टू द क्रिस्टल डिफेक्ट। लेकिन क्या ये संभव है ND इज लेस देन NN, डोनर की संख्या कम हो और इलेक्ट्रॉन्स ज्यादा आ जाए, इलेक्ट्रॉन्स ज्यादा आ जाए, तो ये केस जो होगा दिस इज डीजेनरेसी, दिस इज डीजेनरेसी, दिस इज डीजेनरेसी, कि जितना ही डोप हो रहा है उससे ज्यादा हमको कैरियर मिल रहा है। और ये डीजेनरेसी में कई फैक्टर्स होते हैं, एंड वन ऑफ द फैक्टर इज स्ट्रेन्ड n-type, strained n-type semiconductor, strained n-type semiconductor। strained n-type का कॉन्सेप्ट क्या है कि ये यदि ग्रिड है, ये ग्रिड है, तो स्ट्रेंड जब होगा तो ये ऐसे हो जाएगा, ऐसे। दिस इज स्ट्रेंड, दिस इज द स्ट्रेंड क्रिस्टल। तो यदि स्ट्रेंड क्रिस्टल कहीं से हो रहा है तो दैट विल बी द कॉज ऑफ डीजेनरेसी। सिमिलरली इन केस ऑफ p type material, mathematically this EF P is equal to EV plus KT log NV upon NP, NV upon NP. Here it is NV upon NP, have again three cases. NV is greater than NP, so this is real case, माने जो डोपिंग है ट्राइवेलेंट का उससे कम होल क्रिएट हो रहा है, इट इज द क्रिस्टल डिफेक्ट, इट इज डिफेक्ट, इट इज डिफेक्ट। और NV के बराबर यदि NP हो गया तो दिस इज द आइडियल केस, आइडियल केस। और NV is less than NP, then this is degeneracy, this is degeneracy। और ये degeneracy माने होल की संख्या डोपेंट से कम हो गया, सॉरी होल की संख्या डोपेंट से ज्यादा हो गया, that is called degeneracy। So this factor is less than 1, here this factor is less than 1, तो ये निगेटिव हो जाएगा and this will be positive। And one of the case is here also in case of the strained p-type semiconductor। strained p-type semiconductor का मतलब ये ट्राइवेलेंट है, तो जो स्ट्रेंड होगा वो इस तरह से आएगा, ये स्ट्रेंड ट्राइवेलेंट हो जाएगा, तो इस तरह से ये फॉर्मेशन आ जाएगा। तो दीज आर द बेसिक कॉन्सेप्ट ऑफ डीजेनरेसी। अब इसमें कुछ न्यूमेरिकल्स की बात कर दी जाए, विच इज वेरी इंपॉर्टेंट। कैलकुलेट द carrier concentration। Example, the band gap in silica is 1.1 electron volt and effective mass of electron, that is Mn star, is 0.198 ME electron, and M of N star is 0.95 ME. Then calculate calculate the intrinsic carrier concentration. Calculate the intrinsic carrier concentration. Then solution. The expression of carrier concentration is given as Nn is 2 by h cube 2 mn star pi kt 3 by 2 e raised to the power Ez upon 2 kt. So by substituting the values, 2 upon 6.63 into 10 to the power minus 34 into 2 into 0.198 into 9.1 into 10 to the power minus 31 kg into 3.14 into 1.38 into 10 to the power minus 28 into 300 Kelvin, that is room temperature, exponential minus 1.1 electron volt, that is 1.6 into 10 to the power minus 19 divided by 2 into 1.38 into 10 to the power minus 28 into 300. So by solving this is 3.7 into 10 to the power 15 meter cube. It is 10 to the power. So this Mn, that is carrier concentration of the silica with this electron volt, is this much. So this is about the numerical. So in this way we can calculate the numerical of this. And what about the p type? The p type, that is, if we take the note as note from law of mass action, Ni is 10 to the power 10 meter cube. So this Ni is square is equal to Np into Nn. So what is Np? This Np is Ni square upon Np. So Ni is 10 to the power 10 ka square upon 10 to the power 15. So 10 to the power 20 is 10 to the power 15. So it is 5. So this value is 10 to the power 5 per meter cube. This is per meter cube. So what we find, this value is minority. So this is N-type crystal. This is N-type crystal. The crystal is N-type. You can say this is N-type. N-type crystal. So these are the important things that we have here in case of the carrier concentration and change of the Fermi level. So thank you for this point of discussion.